Hello, everyone. My name is Brad Nicholson. I'm a software engineer on the Instacart storage team. I'm going to talk today about how we do zero-downtime Postgres cutovers at Instacart. So as a brief introduction, at Instacart, we run one of the largest fleets on top of RDS Postgres. We have a bunch of Aurora instances as well, but we're going to talk about RDS here today. And by large, I mean both in physical size, like many multi-terabyte databases, and also high transaction volumes as well. And a lot of those systems also come with very low downtime requirements. And by that, I mean like anything more than a few seconds of downtime for us is problematic. And we start looking at what the lifecycle maintenance of Postgres in that environment looks like, it gets challenging, right? Postgres is a great database, but one area where I'd say it really shows its age is in the maintenance of the system, right? So, it was born in an era where you could take your systems down for 4 hours on a Saturday afternoon to do upgrades and that type of stuff. And that's just not the world that any of us work in anymore. And so when I'm talking about challenges, I mean, like honestly, 90% of what I'm talking about is major version upgrades. It's not the only, but that's the bulk of what we're talking about here, right? So Postgres does not support online upgrades. You have to take your system down when you want to do an upgrade, and that requires honestly non-trivial amounts of downtime. How much it takes depends on, whether you're doing it on-prem, on an EC2 instance. You can do it a little bit faster, but it's still pretty slow. In RDS, you've got a bunch of checks and balances and stuff that come in, which is a good thing. But, you're talking many, many minutes to even like tens of minutes to get the job done. And that's just not acceptable in a lot of cases, right? And then the second case with upgrades that we have to think about is also rollback, right? So the upgrade process itself is actually pretty solid. Like both Postgres and RDS do a great job of protecting you, making sure that everything is going to work in the actual upgrade process itself, making sure that you come back up cleanly if something does go wrong, right? But what I'm talking about is what happens if, the upgrade process goes smoothly and then, the next day traffic picks up 10, 12 hours later. You had a performance regression that you didn't catch in testing. You had a functionality problem that you didn't catch in testing, right? Ideally, you want to fix forward quickly, but if you can't do that, what do? Do you restore your backup from last night, from before you did the upgrade? What do you do about the last 10, 12 hours of data? It's not a situation you ever want to be in. Right. Besides upgrade, we have other things, changing instance classes. We've been moving a lot of things to Graviton. We don't want to take systems down for doing that. System patches, right? And there's a bunch of user level concerns that'll come up too. So the care of kind of the actual schema and data that you actually have. There's a bunch of times when you need to make like table migrations, you need to change your schema. The classic case that comes up with this that we had to deal with in the past, and a lot of people have to deal with is, the 32-bit to 64-bit integer problems, right? In Postgres, when you do that, it's going to take a full table lock on your table. It's going to block all reads and writes, and it's going to recreate the table into a new copy. That can be 10, 20, 30, 40 minutes or longer, depending on the size of the table while your application's down. Can't really do that, right? And there's a bunch of other stuff that comes up with that too. And then there's also, sort of the class of performance impacting operations. So there's things like bloat removal that either require heavy locks, or things like PG repack that take a lot of IO, index creation. A lot of this stuff is non-issue on smaller systems, but we have systems, for example, at Instacart that are so busy we can't create an index on them without causing an incident because we just don't have the capacity. So we need solutions where we can do this on those types of systems. Right. And a common approach in the software world to deal with these sorts of things is the blue-green approach, right? And this comes out of the stateless software world where, especially in the container side of things, your blue system is your live system. You stand up a green system, which is like a shadow copy. And then that's the upgraded version. And then you cut all your traffic over, right? Stateless applications, it's pretty straightforward, but for stateful applications, it's not, because you can't just take a snapshot of your database, stand it up, and then, cut over 12 hours later without all the data getting copied in. And so in Postgres, we have logical replication, which can be used for that. That's a sort of a secondary type of replication that allows us to replicate between database versions, database architectures, and that lets us set up a blue-green system, which simple, right? Well, in practice, no, there's a lot that kind of goes into doing this that gets challenging, right? So setting up logical replication in Postgres, it's not a trivial thing, right? It requires a pretty good degree of Postgres expertise to do it. It's not super hard, but you really do have to know what you're doing. There's a lot of very Postgres specific concepts and a lot of very low level stuff that you have to do in order to do it. You can break things pretty nastily if you get some things wrong. So you do have to move very carefully. It also requires privileged database access. I'm pretty sure actually the newest version of Postgres removes this requirement, but you're not upgrading from the newest version yet. So you have to be a database super user in order to actually do this. And when you kind of combine those two requirements together, you have to really know what you're doing. You have to have super user access. It really does bring sort of the pool of people in most organizations down who can do this work to a small handful. So it can become a choke point in getting your databases upgraded if you have a bunch of them and you've got to have a few people doing them all. Right. The secondary problem that we get to here too is that when you have really large active systems, the impact on setting up a logical replica is actually very, very high. So sort of at a high level, what Postgres does when you do this is the replica connects to the primary just through a standard database connection, and it copies all the data out at front end. There's a few problems you get with that, right? So one, again, straight on the system, when you're trying to copy all the data, you're basically scanning all of your data off disks and pulling it out the front end. When you have very large databases, that process can take many, many, many hours to even days to complete. Process isn't resilient at a Postgres level. So if you're halfway through copying a 10 terabyte table and something happens, it's going to restart from scratch. Like if you get a network blip or something like that, Postgres will not pick up where it left off. So you got a bunch of problems like that. And the secondary problem that you're going to get into is that copy is a snapshot of the data at the time, a consistent snapshot of the data at the time that the copy starts. Once that copy is done, it's got to catch up all of the changes that have come in. And the way Postgres does that is it collects all of your transaction logs on the primary and then uses that to replay that traffic through to the replica. Now, if you have a very high write load system, you're generating a lot of transaction logs very, very quickly. And if you're doing a very large copy, you're going to be generating a lot of transaction logs quickly for a very long period of time. And you're going to get into one of a few problems with that. You're simply going to run out of disk space, or you're going to have to massively over provision your RDS instance in order to have the space for that. If you're in that massively over provisioned space, there's a good chance that you're probably just never going to catch up with logical replication, right? The application of it is pretty slow. So if you have a huge volume of writes coming in and you have a, huge backlog that you have to work through, you can get into a situation where you're just not going to catch up. And frankly, we have systems at Instacart where we can't stand a logical replica up under normal circumstances. There's some lower level stuff too, like it doesn't replicate everything. The sort of main ones that come up are like schema changes won't replicate. So when you have the green instance set up and replicating, if you need to make changes, you have to move very carefully. You have to apply them in a particular order. And then Postgres has these things called sequences, which are the low-level mechanics that are used for auto-incrementing primary keys. Those don't get replicated, so you have to handle those manually, or you're going to get into primary key collisions when you promote the new instance. So there's a whole bunch of things like that you actually have to deal with, right? And then when it comes time to actually doing the cutover, you have to coordinate everything, right? Like it's not just one thing that you move. You have to mess with replication. You have to make sure replication is up to date. You have to move your applications. There's a whole bunch of that stuff that has to happen at a critical point that has to happen very, very quickly and safely. And then we also have the next stage problem that I mentioned earlier, like what happens if we have a problem and we need to roll back. And so the way we've solved this at Instacart is we've solved this with software. We wrote a software suite called Zero-Downtime Cutover, or ZDC as we call it. And what it is it's comprehensive blue-green tooling that allows us to basically manage and execute this whole process end to end. So it has a bunch of safety checks built in. It has a bunch of pre-checks to figure out things like, hey, can you even upgrade this database to the new version? Or do you have schema in there that's not compatible? Because Postgres is pretty bad about changing things between versions on you. And you've got to, update. So we try to find as much of that stuff up front before we do any of the heavy lifting so the teams can fix that and make it as easy as possible. And then we create a snapshot of a replica instead of doing that initial copy, right? And that's the real magic in ZDC. Postgres doesn't directly support saying like, hey, just create a snapshot of my database and then hook it up to logical replication, right? You can make it work, but there's a lot of low-level stuff that you've got to do, and it wasn't an obvious way to get it done. So a lot of R&D work went into figuring out how to make this work and how to make it work sort of cleanly and reliably, right? But that bypasses that whole like multi-day setup, like the huge backlog of replication files. You still get some of that, but it's nowhere near where it is before. Right. And then when you get to cut over, it tightly coordinates everything, right? So we're not just saying like do one thing here. So when it comes time to actually cut the right traffic over, it does a bunch of stuff sort of at a high level, blocks all rights to the application. Well, sorry, before it does anything, it does a bunch of pre-checks to make sure that like we have a high degree of confidence that this is actually going to work. Like if replication is lagging behind, it'll say, hey, we can't do this right now. Those types of checks are in there, right? So when it passes those pre-checks, basically it does a bunch of things. We block all writes to the application quickly. We move all the sequences from the primary to the secondary. We reverse the replication ordering, which I'll talk about in a second, right? And then we automatically repoint all of our applications to the new instance, and we come back up for business, basically, right? And this is all very tightly coordinated. It all happens very, very quickly. It's all written in such a way that if we hit a problem at a lower level during this process, we automatically roll everything back and come back up on the old primary. So even if there's a problem, it's still only, a short period of time. It's not this, something went wrong, and now we got to, get into the terminal and figure out why we're broken and how we'll fix it while our application is down. The reverse replication, that's our rollback path, basically. So really what we're doing there is during this cutover process, before we take in any new data, we're making the old primary a subscriber to the new. So we're on a new version that's replicating back to our old version. And so then what we have is we have the inverse of what we had before. And if we have an next day problem and we need to go back to the old primary, it's actually just another cutover back. So we don't have to worry about restoring a backup or how do we get the data. Everything is back on the old copy. And so we look at kind of the results and impact. So like the pre-ZDC world sort of stretches between like back in the days when we didn't even really have logical replication in Postgres, right? That was, click the upgrade button, be down for an hour and come back up. And that was a horrible situation to be in. But, that's sort of where the state of Postgres was at the time. And then once, PG logical extension that was written that can do logical replication, the native replication came in, we were able to do some of this stuff manually without the clever snapshot cutover initially, and then doing that clever snapshot cutover manually. Those were complex multi-page cutover plans that literally like one or two, maybe three people in the company could do. They were all individually written and reviewed. They took a ton of engineering time to plan and execute. And again, took, initially like an hour plus down to like many, many, many minutes, not the sort of really quick stuff. And now with ZDC, we can create an upgraded replica. It takes, in general, a few hours to spin it up and get it caught back up. It can take a little bit longer for the really, really big and large systems, a little bit less for some of the smaller ones, but it's not a problem anymore, right? When we do a cutover, our average downtime is a few seconds. That mostly presents as a connectivity blip to our applications. All of our traffic is going through PG Bouncer and PG Cat, so the actual application cutover is just, switching the connectivity there, and it's good about not breaking the connections for us. We've done, I don't even know how many we've done at this point, but over the past 2 to 2.5 years while we've been using this tooling, we've done dozens of successful cutovers with it. We've saved a ton of engineering hours with it, and we're saving even more. We're in the process of actually automating the process, so it's no longer calling all of these individual steps independently. It's, clicking a button or calling an API call in our internal software interface, so pretty much anybody in the company can do this. And it's become a core tool at Instacart. It's very well used. That's my presentation. If we have time, we'll take some questions.
We did have one in chat, but looks like Richard was all over it. Is there any other questions? Okay. Feel free to come off mute or post it in chat.
Yes, I had the same question, whether it could be open sourced and be used by other customers.
Yeah, we're not opposed to open sourcing it. We actually talk about it a lot. The difficult part about open sourcing it is the cutover component is very tightly tied to our internal software tooling. So how we manage all of our configurations for the bouncers and the PGCAT instances, it's all in a very sort of Instacart specific internal tooling. And that cutover portion assumes that that's there. So in order to open source it, we would have to sort of strip that out, make it a little bit more generic. So it'd be like a non-trivial amount of work. So yeah, I won't say no, but it's not something where we could just easily put it up and open source it. We do talk about it though, and there is some interest in doing it for sure. I see the other one there. Do we need to redeploy the services after cutover? No, we don't actually. So all of our connectivity goes through either PG Bouncer or PG Cat, which are the sort of standard. PG Bouncer is the standard Postgres proxy, and PG Cat's a newer one that we're working on. And basically, what happens is you just change the configurations in those so that it points from the old instance to the new instance, and when you reload them, it basically, what happens is the connections to the proxies don't break from the application to the proxies don't break, they're maintained, but the connections from the proxy to the database get broken and pointed to the new ones. So the applications don't need to reconnect. They'll experience a brief blip where their connections look like they've reset from underneath them, but there's retry in all of the applications. So you basically, it's going to say, oops, there was a blip, and it'll retry the connection and it'll get back up on the next instance. So, and that's actually part of where the magic of our internal software center helps us out there, is because, like, you know, we may have a dozen different applications connecting to a given database, and it moves all of them together very quickly, right? And they're going through different proxies in different places. How do we know if the new cluster is in sync? It's actually pretty straightforward. So there's a couple of things, I guess. There's, like with Postgres, you can monitor the replication lag pretty straightforward. So when the replication lag goes down to 0, you know that you're in sync. But the other thing I didn't mention, as part of the checks and balances we do, we also have data validation built into this, so that, like, once the replication gets spun up, it validates that, like, we're actually a proper copy, that we didn't miss any data, because we have had bugs in testing and stuff in the past with that initial snapshotting point where something doesn't go correctly, or we've hit weird Postgres bugs where it's happened. So we really make sure that that data matches, especially around that sort of snapshot and replication window. We have some pretty tight data validation in there that will alert us to problems. Aurora does not solve any of these problems, no. So Aurora has zero downtime patching, which supports minor versions, but you still have a whole problem of major version upgrades with Aurora.
Brad, Aurora's got a slightly different way that they manage the LSNs. Is that, if I recall correctly?
It does, yeah. So Aurora actually has the proper things, and we don't have the support built into Aurora yet, but we did the process manually when we were sharding one of our databases to spin it up off a snapshot. So we're pretty confident in the Aurora side of this working as well, but we just haven't built it into our tooling. The tooling has a bunch of sort of assumptions of RDS specific stuff because it was written in the RDS only days. So we just need to tease that apart a little bit, but pretty confident that the same approach works with Aurora.